Introduction of Orifice coefficient. The Orifice coefficient experiment investigates the behavior of fluid flow through an orifice or opening. Since energy losses occur during flow, correction must be applied to the velocity and discharge value obtained from Bernoulli equation. Therefore, the coefficient of velocity, contraction, and discharge are determined to accurately describe the flow characteristic. These coefficients are essential for evaluating the performance of the orifice and estimating the fluid flow rate through it. Theoretical background. An orifice is a small opening that allows fluid to flow due to a pressure difference. The flow is commonly analyzed using Bernoulli equation, which predict the theoretical velocity and discharge. However, friction and turbulence cause energy losses, making the actual flow lower than the theoretical value. To account for these losses, the coefficient of velocity Cv, coefficient of contraction Cc, and coefficient of discharge Cd are determined. These coefficients help describe the actual flow behavior and improve the accuracy of flow measurements. The orifice coefficient experiment is conducted to determine this coefficient and study fluid flow through an orifice.
Now, let's see the apparatus. We have hydraulic bench, reservoir, 4 mm orifice and 8 mm orifice, prop board, and meter rule. Let's go see the procedure. Firstly, we measure the diameter of orifice. The diameter of orifice is 4 mm and 8 mm. Place the orifice 4 mm diameter at the tips of reservoir. Next, turn on the hydraulic bench, then adjust the water flow. Adjust overflow until the water fills at the level of height 1. After that, we measure the height. To record the data, firstly, we need to adjust the needle of the probes to be just in contact with the water jet. Next, record the needle height of the probe profile on the paper vertically. Then, we measure the horizontal line. Lastly, measure the flow rate Q that the water exits through the orifice, and the time is recorded for each 5 liters of water. Repeat this step by using the 8 diameter of orifice.
Hello, my name is Natasha Nabila binti Muhammad Mubarak, and I'm going to discuss about the result analysis and also the discussion part for this laboratory. So here's the table that we're supposed to fill in. First, we have the diameter of orifice. The first one is 0.4 cm and the second one is 0.8 cm. So we have to take head level measurements, the distance for y and also distance for x. So by theory, orifice trajectory equation is x equals to 2cv set yh. This formula is kind of similar to the linear equations, which is y equals to mx by c. So by comparing both of these, we know that x directly proportional to the set yh. So we can actually find our coefficient of velocity by dividing the gradient m over the 2. So after tabulating all the data inside the graph, we gain our linear equations of the bi-strand line. So here, by comparing the linear equations, we know that for 0.4, we get gradient is 1.7584, and for 0.8, we get 1.7747. So just substitute the value inside these equations. So for coefficient velocity of diameter of orifice for 0.4 cm, we get 0.8792, and the coefficient velocity of diameter of orifice of 0.8 cm, we get 0.88735. Next, this table is about flow rate. We are trying to find the coefficient of this discharge. So like usual, diameter of orifice in meter, area A, also in meter, calculated using pi d square over 4, head levels in meter, volume in meter cube, time in second, and we calculate the flow rate Q actual equal to volume over time. And by using the equations and comparing it to the linear equations, we know that Q is directly proportional to the A set 2GH. So we calculate the area times set 2GH, then we plot graph flow rate Q versus A set 2GH. So by finding the trend line, we know that CD is actually the gradient. So our coefficient of discharge is equal to the gradient M. So for 0.4, we obtain a 0.5556, and for 0.8, we obtain 0.6667. So for coefficient of discharge for 0.4, we get 0.57, and coefficient of discharge for 0.8, we got 0.67. So next, we're going to find the CC, which is our coefficient of contractions. So by using the CC formula, CC coefficient of contractions equals to coefficient of discharge over coefficient of velocity. So for CC 0.4, we got 0.65, and CC for 0.8, we got 0.7. I will discuss the result of the hydraulic orifice experiment. Two orifice diameters were tested, which were 0.4 cm and 0.8 cm. The larger orifice produced a higher flow rate because its larger opening allowed more water to pass through. The coefficient of discharge also increased from 0.57 for the 0.4 cm orifice to 0.67 for the 0.8 cm orifice, showing that the larger orifice was more efficient. Both values are less than 1 because of energy losses caused by friction, turbulence, and flow contraction. Overall, the experiment shows that increasing the orifice diameter increases the discharge, and the result agree with hydraulic flow theory.
Finally, for the conclusion, the orifice coefficient experiment was successfully conducted to determine the coefficient of velocity CV, contraction CC, and discharge CD. The result showed that the actual discharge was lower than the theoretical discharge due to energy losses caused by friction and turbulence. The calculated values of CV, CC, and CD were within the expected range and demonstrated the flow characteristic through the orifice. Overall, the experiment achieved its objective and verified the relationship between theoretical and actual fluid flow with minor differences caused by measurement errors and experimental limitations.